Ladies and gentlemen, or according to my YouTube analytics, gentlemen. Welcome to another Solana tutorial. Today we're gonna have a look at writing Solana programs in assembly. Yes, the day has finally come. We're doing this now. This is gonna be good or horrible. I don't know yet. Have never tried, but that's the fun of it. So we usually write programs in Rust, right? Easy. And then we had a look at writing programs in C, which was also possible, right? And now I want to have a look at writing programs in assembly, not because I suggest that you write programs in assembly, but because I want to prove that it's possible and make some points why in some use cases it could be beneficial, but for the most part, really, you want to write programs in Rust or C. Assembly is like, who codes in assembly? What programs are written in assembly? Like, not just Solana, but like in general, who does that? Nobody. It's not really a thing, is it? So why am I so excited about this? Well, on the one hand, because this is really low level now and I just want to learn and see how it works like behind the scenes. So really this is a learning journey for me. But you might even be able to use this productively for tiny programs. When you have a program that just needs to do one very specific thing and it's so simple that you can code it in assembly, then maybe you want to code it in assembly. Or another use case could be that you have a function where you have a very efficient assembly implementation for it, and you basically want to just get that into your program that you've otherwise written in C or Rust. That could also be an interesting thing. Or the third thing that I can see why knowing about assembly and how Solana programs are really written is that you can have a look at existing programs and really see what they're doing. Because that is on-chain data. You can't just have a look at that. You can't have a look at the C code or the Rust code because that gets down-compiled to assembly. But you can just disassemble the bytes and back you have the assembly code. And you can read it and have a look at that. We're not going to do that today. Today I just want to see how I can write a simple program and deploy it. And that's definitely going to be challenge enough for a day. So yeah, I mean, let's get started, shall we? And write a Solana program in assembly. This is both stressful and exciting at the same time. I'm like, I have no idea how I do this, but I really want to do it. So let's do it. Let's go. Write a Solana program in assembly. Can't be so difficult. Let's just Google that and see what comes up. Jonas has a video. I have videos, but that's not assembly. So essentially you can just watch his video. I mean, you can do that, of course, but I don't want to do that. I just want to find where he has the... there. Solana developer CU optimizations. There they have assembly examples. Install Solana LLVM. Whoa! Solandy, that's what? That's me. Yeah, I'm referenced here. I didn't even know that. Serialization, does it say anything about there? Native versus Anchor versus assembly. Right, so he has a counter example that uses 4CU. That's amazing. In C, you can also get it in 5CU. The assembly example is a very simple example that does not include any checks or error handling. SPF assembly macros. Writing programs in assembly. To get started, you can watch this video guide. Is that what we just looked at? Yes. I want to get to there. It's really difficult to learn in video, says the guy who makes YouTube videos as tutorials. First, there should be docs, and then I make videos about stuff for people to more easily understand, who have difficulty with just docs or need someone who reads it to them. Solana Program Rosetta by John Cinque. I like this guy, so whatever this is, I want to try it. It's a great tool to get started with writing programs in assembly. It comes with complete bank run tests. I don't think I want to test, but it's nice that we have that. Also contains examples in SIG and C. Or we use the SBPF by Dean. Wow, then we get a SBF init, build and deploy. I mean, that seems like simple. You should start by reading the docs on exact memory layout of the entry point. We did that last time, I think. The entry point, we had a look at the entry point last time. Yeah. We did do that. We know that. I have a video on that. And that, yes, that's in the video. So yeah, we know that. The memory layout and entry point, we know that. That's why we had a look at this. Repository links and tips for assembly programs. Oh, that's also from Dean. And there's even a VS Code extension. Helps with autocomplete and syntax highlighting. So it kind of looks like the thing from Dean is the thing that I want to use. But I do want to have a look at what John has. So there's a Solana program Rosetta. Transfer Lamperts in assembly. His S file looks like this. I mean, that's pretty much, yeah, that's what I want to do. I mean, that's simple enough. We have to install Solana LLVM, make it, moves 5 Lamberts from source account to destination. 22 compute. I mean, let's not make this too complicated for us. Let's check this out. Just want to check what it's doing. It's downloading from John Jinko's GitHub. SPF LD, he's manually writing this. So that's essentially what I think that's essentially what we write into the programs additionally to the program code, because we have the sections of the program, the text, data, sweet. I think I want to try John's thing if I can get that to work. And again, it defines a global entry point. Nice. Yeah, we're gonna do this. I've decided we're gonna do this. Let's go. So step 1, clone me this Rosetta and then open this Rosetta. We trust John. In John we trust. Okay, I mean, this seems safe, right? Downloading something from here. Whenever I have code from the internet that I just run, it's like, oh. Okay, yes, I trust it. Let's install Solana LLVM. The LLVM is Solana on-chain programs are compiled via the LLVM compiler infrastructure to an executable and linkable format containing a variation of the Berkeley packet filter bytecode. So that's the bytecode. We have the SBF, so the Solana Berkeley packet filter, which provides an efficient instruction set. So those are the commands that we have available. So those are the things that we will be able to write in our assembly code. Still didn't manage to find what LLVM stands for. Itself is not an accurate, it's the full name of the project. Has little to do with virtual machines. Okay, let's just accept that that's the compiler infrastructure. So basically, we want a compiler that can compile to this format. Or this is a form of compiler that compiles this format. Whatever. Or it is a collection of compilers that adhere to a certain standard or something. Yeah. Can be executed in an interpreted virtual machine. Now that we haven't figured out what that stands for or figured out that it stands for nothing, let's just install. In version 1.43, it will be fine. 300 megabytes. Wow. The hell am I downloading here? Oh, and here it writes where the sections are. Now we're unpacking. 1 minute and 1 second. Nice time. And then later we're gonna write an assembly program like this. Which, okay, I get it. It's not nice in Visual Studio. I don't have any autocomplete or anything. But that's alright. Not ideal, but okay. So, tools will be available at Solana LLVM. Okay. So here I have the SPF LD, where it basically just, yes, wrote that. Yeah, and then main S to main O, then the main O to transfer Lamperts SO. Makes sense. So this is compiling and this is linking, I guess. But what do I know? I'm just gonna check if I can run this. So the transfer Lamperts example, make this. There's a folder assembly and here I can make this. I guess that worked. Now I have an output directory with the O file, which I don't care about, and the SO file. Let's list me the output file is 600 and then 1400 for the SO file. So we will still need 2 transactions to deploy this, but I guess we can deploy this. Let's see. So how would I do that? Solana program deploy, and then the path to the SO file. And then probably we would like a key pair. Hold on. Keygen starts with assembly. There you go. And we're gonna say program ID is this assembly key file. Deploying. Sending 2 transactions. And the program is deployed in 2 transactions. I watched Jonas do it in 1 transaction, so there is the possibility to have the program be even smaller. Not with those tools, but we'll get there. Starting slow, starting slow. Okay, so that's a thing now. We have that program. Now we kind of want to call it. And I had a script once. Just gonna do the same thing. Create an account with 0.1 lamperts. You don't have any space. The instruction data it should ignore anyway, but we can leave it in there. Let's try this. Let's call this program ts node call assembly. Look at this. It worked. We called the program. And guess what it did? It probably oh no, it didn't. Oh, we're in mainnet. It probably transferred lamperts. It transferred 5 lamperts. So our assembly program used 21 compute units. 21. Wow, that is not a lot. That is not a lot. So the total is 171 then? Yeah, 171. Fun. And we transferred 5 lamperts from here to here. Great that we can do that, right? But all we did is deploy this program that, let's be honest, we didn't write. We let John write it and then we just used it. So what's the point of that if we don't learn what it actually does? So let's learn what it actually does. It has this global entry point. I guess that's how we are found. That's what the runtime then calls. And to understand all of those things, maybe we want to have a look at the instruction set. The eBPF spec, it has 8 bits for the opcode, 4-bit for the destination register, 4-bit for the source register. Most instructions do not use all of those fields. Unused fields should be 0. Yeah, so there we see we use several registers and we have 4 bits to access the registers. I don't know how many registers we actually have available. Wait, 4-bit to the power of 4 is 16. Oh, that makes sense. So in this architecture, we have 16 registers. That sounds like a regular CPU where we have 16 registers. Oh, that's fun. So the ALU, the arithmetic logical unit, where we can do, calculations. Now, if you don't understand assembly, if you look at this and you're like, what the hell is that? That's not at all source code that I'm used to. Don't worry, I got you. I made a video where I talk about the basics of assembly and I went through Von Neumann architecture for a bit. Just in case you need a refresher or you've never heard about that, I made a separate video that you can watch in case you're lost here. Because I'm expecting that a lot of you will be lost here, so that's why I made that. But yeah, in that video, that simple computer that we had, wait, I show you again, it was the little man computer. This guy basically had 2 operations in the ALU, which is add and subtract. And here we have a bunch more. We have add, and that's the mnemonic. That's what we would write here in our program. Do we have an add somewhere? We have an add here. That's how we write it. Add this and this. And the structure is always opcode, register, and immediate. And not all of them will be set. So for instance, for the add, we have the destination and the immediate that we use for this opcode. And what it does, it adds to the destination the immediate. So for instance, we could say add to this register 42, or whatever we write into the 32 bits intermediate. There's also an add that adds the source register to the destination register. Then we have a sub, same with the value directly or with a register. Then we have a multiply, a division, an OR, so logical OR, logical AND, a bit shift, right shift, so bit shift left, bit shift right, a negation, modulo operator, XOR. We can move, so basically copy, move the source into destination. And we have arithmetic shifts. Those are logical shifts, logical right shifts and arithmetical right shifts. The difference is what the highest bit will be when you right shift, because at the logical one, basically it just gets shifted and the uppermost one is 0. At the arithmetical one, if the uppermost bit is 1 and you shift it, then it's also 1. I think that's the difference without reading up on it. So don't quote me on that, but I think that is the difference. That's why we don't have a distinction in the left shift, because in the left shift it doesn't matter. There it will always be the 0 coming in. But here it makes a difference, because if you have negative numbers starting with 1, then you might want to keep them negative and just still bit shift. Anyway, so those are the operations that we have for the ALU. That's all the mathematical stuff that we can do. And then what else do we have? Oh, we can do 32-bit arithmetic. This was 64-bit arithmetic. Okay, makes sense. If we're using a 64-bit architecture, then that's the default. And we can do specifically for 32-bit architecture, but let's ignore that. Oh, here it even says explicitly sub 64, move 64. And then we have the memory instructions. Those are also important again, where we have the load. The LD stands for load. You might be familiar with this. So load something into a register, load into the destination, the immediate. So if I have LDDV register 142, then I load the value of 42 into there. And the DW stands for double word, and a word I think is a 32-byte number. So double word is a 64 then. Or is the word the 16 and the double word is a, I don't know. Typically consists of 2 consecutive words or 64 bits of information. But our immediate is only 32 bits. Yeah, different ways how to load stuff. I mean, this is complicated, let's be honest. And then we get to the loading from somewhere in memory based on what is somewhere in a register. So we load into our destination register whatever is in the source register plus an offset. So now we basically have a pointer inside our source register, not the actual value. And then we can do the same with the storing. We store a word to the memory address that is inside the destination register. That's how it's usually done. We usually have the memory location in a register, and to that location we write what we want to write. And there we see the things. The W is the word, that's for 32. The H is for, so whatever H is, probably also has a name. I don't know it. Word is 32. A byte is 8. Double word is 64. And then once again, the storing with pointer. This was storing directly what we have in the immediate. No, we always store it with a pointer. But here with the X, we store what is inside a register. So what's in the source register, we store it to the memory location that is inside the destination register. And we can have an offset. Yeah, so the offset is another thing that we provide here. So we have the opcode, destination, source, offset, and immediate. We're just trying to understand this because that's the stuff that we need to know in order to actually write assembly, because those are the things that we can do. And when you actually write with that, then you will appreciate actual programming languages where you can write, proper code with variables and stuff. Anyway, then we have the branch instructions. That's also important because that gives us conditionals. We can basically just jump add, or whatever the A stands for, where we add something to the program counter. If you don't know what the program counter is, we also discussed that in the previous video. So basically just skip the next few instructions, and how many instructions we skip is written in the offset. Then we have conditional jumps. Jump if equal. So if the destination and immediate are the same, then we jump for this offset. And then the same with the source. So if two registers are the same, jump if it's greater than, once with data, once with what's in a register. Then jump if it's greater or equal, if it's less than or equal, always in the both versions. Jump if set. So with a logical AND, if any of the bits match, if any of the bits are set in both, then we jump. Again, we see a lot of possibilities with this, but you gotta do a lot of brain work to actually properly use that. But that's usually what compilers do for you. You just write your nice C code, and then the compilers find the right instructions that are most optimized to do that efficiently. But I mean, you can write it manually, nothing against that. And then we have a jump if it's not equal. We have a jump with a signed greater than, and with a signed less than, and so on and so on and so on. And we have a call. Don't ask me what that is exactly. That's probably setting the program counter to a specific address, I guess. And we have the exit. And upon exit, we return what is in R0. So the R0 is our return register. We have several registers, but R0, what's written in there when we exit, will be taken as the return value. Cool, and that's it. That's all we can do. Back to our program. Now we totally know what all of that means, right? We load a double word with X means from register. So we load into register 2 what is in register 1 plus offset 0. So somehow, wait, that's what we're doing. So we write into register 2 uint64 from source plus offset. So somehow magically in our register 1 is the location of the input. So in register 1, I guess we already have the pointer for the input. You know, when we had the C code, that thing, that pointer, when the entry point is called, we have this input. And I guess our register 1 is set to this very pointer. Let's just assume that that's the case, that R1 is the input pointer. In our register 1 is stored the location of the memory where the input starts. So the +0 gets us the number of accounts, because at the very input pointer we have the number of accounts. And then what we do, we jump if not equal. So if what we just read into R2 is not the immediate 2, then we jump to error. And here we have one of those labels that we define later. So basically, wherever in the code this will be, it will be replaced, right? So that's just a label. So it will jump to the error if what we read is not 2. Then we load again a byte, get the first account. We check if it's a duplicate. Shouldn't be a duplicate. Let's check. So if it's not exactly 0FF, and we also know what that means, we're checking if the first byte is 0FF, meaning that it's not a duplicate. And if it's anything else than that, if it's not equal, then again we also jump to error and say we write into our register 1, so that's then the error code, into the return register, and we exit, which is also an opcode, this one, that finishes. So that's that. We check if it's a duplicate. Then we get the source lamperts, and this is fun. I mean, here he writes a lot with a +++, and this is exactly, these are exactly the bytes here. So basically we're skipping, this is 8 bytes, +32, +32, 8 +32, +32. And the first 8 was the number of accounts. That's the source lamperts that we now read into R2. Then the account data size we read into R3. That's the next 8 then. And then we move the R1 into R4. So that's basically a copy. Then we add all of that. So that's all of this plus the padding plus another 8. That's for the rent. What was that? The rent epoch. So that's calculating the end of the account. Not really adjusting for the correct padding in case the account data size is a bit odd. Oh no, that's here. Then he adds the actual account data size. So the R3 that we read here, it also adds to the R4. And then clears the high bits. So just the lower bits of this one. Oh, that's smart. It just looks at the last 7 bits. And if it's 0, then we jump for 1. So we skip this. So basically we don't add another 8 bytes. Then we clear the low bits by adding -8. Or by ending -8. -8 is all ones except for the lowest 7 bits. This is so fun. I understand it, but it's really difficult to understand. If there wasn't like comments like this, I would not understand it either. You need to think in bits here, but it's fun. And then we're basically done with that because we've added the padding. So that means now in this register, which one was it? R4. In R4 should now be the pointer to where the second account starts. So the second account now starts at R4 and then we load a byte again. So we do the same thing as here for the first account for the second account. We don't allow duplicates. Again, to make it easy, that's the same how I wrote my decode function, just not allowing duplicates. So we error if it's a duplicate. Again, we get the Lamperts. We write that one into register 5 now. And the other Lamperts we had in register 2. And then we basically subtract from register 2 5 Lamperts and we add to register 5 Lamperts. And now they're just written in the registers. Now we need to actually write them back to where they belong at that pointer location by storing the double word, the word that is at the register R2. So that's why we have that X. We don't want to write what we want to store, but we want to store what's inside the register. So we store what we have in the register, a double word, so 64 bits. And we store it to R1 plus 8 plus 8 plus 32 plus 32. Because again, that's the layout here of those accounts. Because that's where we want to write it to. So we have 8 plus 8 plus 32 plus 32. And then the same here, except at the R4, that was at the very start of the account. So we were like here. So we just need the 8 plus 32 plus 32 and not the initial 8 bytes as well. What is in the R5 is written into the pointer here or into where that pointer points. That's so cool. And then we exit. And that's the program. Wow. Wow. Really, really cool though. I love this. But we already see coding in assembly is difficult because basically we need to store all of that stuff in registers. We need to remember what we have stored in which register. And then we're limited by the amount of registers we have, namely 16. And so, yeah, that is tough. But now, to prove that I understand what is actually happening here, I want to write myself my own program. The same thing that we did here when we forked this and we added the functionality that we read the amount from instruction data. That's what I want to do. Let's code some assembly. Okay, I mean, this is already quite a big, well, it's tiny, but it's like, it reads like big. And John already made assumptions on what he allows and what he doesn't allow. Like he doesn't allow duplicates, same as we did last time when we worked with the entry point and optimized our entry point. But I can also optimize that more by saying I don't allow data either, just so I don't need to copy that code, because, you know, duplicating code like this is difficult because I need to think of what was the register. So I'd rather just get rid of some, because let's say I don't want to allow data size anyway. So we read into R3 the account data size. We don't need that because we assume it's 0. Then we move into R4, the R1. We need that, yes. We calculate the end of the account. That also works. We don't need to add the data size because it's 0. Actually, should I error if we have data? Yeah. We jump if not equals what we have in R3, 0. If in R3 is not 0, then I jump to error. Okay, so we read the account data size, but we don't allow account with data. Cool, so then we don't need the add. And then we also don't need to check how much padding we need to add. So we can save all of that because we know that we don't need that. And also the clearing the low bits, we don't need that. Boom. Then we get the second account from the R4. We don't allow duplicates. And just to prove that that still works, I'm going to deploy this version and I'm going to change something else. I'm going to change this to 6, just so you know that it's actually deployed, my version now. Once again, make this, and then we once again deploy this in 2 transactions. And then we once again run this and see, it worked, and we transferred 6 Lamberts. And it still all works because my accounts have 0 data. If I had an account that actually has data, then the transaction will fail. And let's see how it fails. It fails with custom program error 1. Why 1? Well, because that's what I wrote into the return register. I can fail with custom program error 42. Wow, it also builds very fast because it's literally that little bit of code. Deploy it. And now it fails with custom program error 42, which is 2A in hex. So that works. Cool. Good. Back to my code. We have the same thing where we basically, you know, have a static value here, but I want to read how many Lamberts you should transfer. So we need to find out where that is. R4 holds the start of the second account. I need to write down what I store where, because otherwise I get confused. R1 has the start of the input. R2 has the number of accounts. I didn't write anything else into there. Or did I? Yes, I did. Yeah, R2, whoops, I overwrote this then. Lamberts of account 1, or let's call it source. R3 had the data length, but I don't need that anymore. R4 has the start of the second account. R5 has the Lamberts of the second account. So basically R3 I can still change, and then all the remaining registers as well. So let's do R6, the start of input data then. So, wow, assembly is so difficult. It takes some mental effort to write assembly. So first, if we want to write the start of the input data, so first I write what we already have in R4. So I move into R6 from R4. I basically copy this into there. And then I add into R6, well, basically this again, except the first 8 we don't need. It's just 8, 32, 32, 8, 8, 0, 10K, 8. 8, 32, 32, 8, 8, 10K, 8. Yep. So then R6 points to the end of the account. We know we have exactly 2 accounts. And then comes the number of bytes for instruction data. I write that into R3 again. So that's my instruction data length now. I will load from the address of a register a double word into R3. and I read from register R6, because that's the start of the input data, +0, read input data length. And I could make a check now that this is exactly 8 or something like that. I jump if it doesn't equal what I've read here in R3. If it doesn't equal 8 bytes, then I jump to error as well. And I could say at least 8 bytes or whatever, but no, I say exactly 8 bytes. And then I'm gonna actually read the bytes, and I'm gonna read them into R7 because I still have registers. Like if you write a bigger program, you're gonna run out of registers. You can't hold that much data. You need to write it somewhere and then load it again. But again, that's instructions that cost CU. But that's also a way to optimize, right? Put it in the right such that the registers are like that's what the compiler does. It puts it in a way that the registers can be efficiently used and you don't need to think about that. But if you want to think about that, maybe you can be more efficient than the compiler. Who knows? Anyway, so in R7, I want to write the amount of Lamperts to transfer. So load a double word, because 8 bytes, to R7, R6 plus 8. Because we skipped the one double word, that's 8 bytes. Cool. And then I don't need a subtract 64. I need a... Oh, it's called the same. I just need to specify the register and not the immediate. Okay. So instead of 6, I subtract what's in the register number 7. And then I add what's in register number 7 to R5. And then I store those two back where they belong, that I didn't change, and then I exit. Let's save that. You think that's gonna work? We will see. Let's deploy, fix our script back to no space, and then we run it. A transaction went through, so I didn't error, but did it do the thing that I wanted to? What did I want? My instruction data was this, it was 8 bytes, and it was 256 plus 44, what was that? 303. 303 Lamperts I'm expecting it to transfer. We called this program with this data. It consumed 22 compute units. And what did it do? It transferred 300. Wait, did I say 300? 250. Yeah, we said 300. Yes, because 56. Sorry, it was 300. Yeah, because 303 would be this. There, now it's 303. And it works with the entire byte. Can transfer 9,999,000 Lamperts. And if I do that, insufficient funds for rent. Oh, yeah. Because then I would only have 1,000 Lamperts in there. I need to have at least 89,000. Let's keep that many. Then it should work. Nope. Oh, 1, 2, 3, 1, 2, 3. There's another 0. Okay. Transfer 9 million back. Now it should work. There you go. Now it works. And now it looks like I just transferred 0.001 there because I transferred it back. I can also transfer it to another account, those 9 million. I don't need to transfer it to the signer. I can transfer it to... I'll just transfer it to my program. Actually, then I could just... because I can. Look at that. Wait, no, I cannot because that's not writable. Program address may not be writable, which is both invoked and marked writable. Okay, so you can't invoke it and have it writable at the same time. Only one of those. Okay, fine, I'll transfer back to this account then. There, then you see it better. This account now got +009 because that's the exact amount I transferred. Because my assembly program reads the entire word, so the entire 64 bits. It's actually easier than I thought to work with, you know, double words, big ints. Big ints is just a double word, and the registers are big enough to hold big ints. Amazing. Yeah, and that's how you write assembly programs. essentially. Let's test that it would fail if I don't have enough bytes, or even if I have too many bytes, it will fail. There you go, custom program 2A. We don't know why exactly, it's not in the logs, but we know why because it's not exactly 8. And I'm checking for exactly 8. I make sure it's exactly 8 bytes of input. And fair enough, I could, ignore that and I don't even need to read the entire input data. I could remove that, save that, make that, deploy that, and then this thing with the 9 bytes would work as well. Wait, not yet. Is it deployed yet? But now. There you go. Now it works. Proving that I understand what's happening. Right. But I'm gonna hold it. I'm gonna get it back. Nice. That's it. It's very not easy and not glamorous and a lot of work for a little pay, but then also you get to deploy programs in 2 transactions and you can run stuff in 20 computes. 20 computes is what it takes to transfer that amount of Lamperts from one account to another. It's not much. With this efficient implementation, because I skipped another check now, which also saves me 2 compute units essentially. So basically, more or less, every one of those instructions is 1 compute unit, right? Let's see. Because yeah, I have 20 lines of code minus those 2. That's fun. 20 freaking compute units for a transfer. With C, we still needed 160 or something. And then we optimized it to 130 with the other entry point. But hey, compare that to 20 in assembly, we're doing no check. Well, no, it's not even that we do no checks. We just do not many checks. So this program is easier to hack than others, but it's super efficient. Yeah. Oh man, oh man, oh man. I don't know if the auditors like it if you write stuff in assembly, but efficient it certainly is. Certainly is efficient, I tell you. Yeah, what else do I want to say here? That's it, right? Okay, one last thing. From this account to my new account, transfer 9 million Lamperts, but I don't add the create instruction, so that it's just this transfer. There you go. Because then it's just this transfer. Because that looks so fun. It's just this transfer that transferred from this to a new account. And then the entire transaction has 20 compute units consumed. 20 of 200k. That just looks fun. And it works. It works. It does exactly what it's supposed to do. Simple, small little program written in assembly. All right, I mean, we just scratched the surface of what is possible with assembly. We just used John Chinque's tools. There is a lot more that we can have a look at. More tools, more example programs, more optimizations. Let me know if you want me to have a look at that stuff. Demonstrating extreme binary optimization. This might not have been the last video I make about coding in assembly and SBPF. That could come back. I could come back to this topic because it's just so much fun. I mean, a transaction with 20 compute units is just so much fun. Good. Thanks for watching and being interested in coding programs in assembly. Let me know if you want me to do a more complex program. If so, what exactly? I mean, I don't want to do too complex because, again, too complex is too complex. But, I mean, it is kind of fun to work with assembly, let's be honest. It is so efficient. 20 compute units for an instruction, that's pretty wild. And you can probably optimize it further. Jonas had something with 5 compute units. Hold on. One last thing. Let's make this to more of a minimal example. Let's not check the accounts. Let's not check if it's a duplicate. Let's just get the source Lamperts. Let's not even store that into R4. Instead of R4, we take R1 plus that. And then instead of R6, we use R1 plus that, which doesn't read nice, but should be more efficient. The compiler or whatever, when I make this, it will make this into one number that it writes into the offset, because that's 16-bit, it should manage. And then we don't need to have those in the register. Saves us some space. Let's make it, deploy it, and check if it still works. Oh, now I can't transfer 9 anymore. Now I will transfer 69 Lamperts because I don't have that much on the account anymore. Access violation in unknown section at address 48 of size 8. Okay, I messed something up. Shit, we get an access violation. So we try to read a byte. No, size 8. We'll try to read a word at 0x48. Which is 72. Oh, yeah, here I'm still using R4, which doesn't exist. Instead of R4, I of course need to use R1 plus this. Again, it's not nice code, but it will do. Try again. But it's nice to see that we got an access violation. Yeah, because R4 was 0 and then, wait, what was standing there? We had R4 plus 8 plus, so that's 64. That was 72, right? 32 plus 32 is 64 plus 8 is 72. Yeah, that was my access violation. Now let's run this. Success, but we have an account with insufficient funds for rent. Oh, because we transfer 69 Lamperts to a new account. Oh, then let's transfer to the same account we've already transferred to. Okay, there we go, that works. We transfer 69 Lamperts from here to here. In how many compute? 8! 8 compute units, man! We transferred Lamperts in 8 compute units. And I even define how many it were. Oh, this is great. I love this. 8 compute units. Did you ever send a transaction consuming 8 compute units? I did. And yes, a counter is easier. You can do it in 5. Wait, what did Jonas say? He did a counter in 4. Yeah, great, because a counter you only do 1 account and I do 2 accounts because I need to change the Lamperts on both. So I guess that's why. Plus I read the input data. So yeah, it's I don't think you can get much more efficient than this. Also, this is not only efficient, it's also highly insecure because again, I don't do any checks now. I don't do any checks that it provides the right accounts. I don't do any checks that, anything. I just do. I just read how much I should transfer and then transfer. And if I also wouldn't care to read, like if I were to statically load instead of R7, 69, 69, or let's do 42, then I probably save another compute and then I do it in 7, I guess. Let's see. Yeah, going through. This one, 7. And I transfer 42 Lamperts. But this is hard-coded now again, which is boring. I prefer the other way. But yeah, 7 compute units is not bad. And there you see how you can get to 5, basically by not doing this one and this one, which is for the other account. If you just, load it from one and write it back, then you can save another. But it makes perfect sense. 1, 2, 3, 4, 5, 6, 7. And if you save that and that, then you get to 5. But I need to add and subtract, so yeah, because otherwise the runtime complains that I'm making up Lamperts. Now, I'm just curious, what would happen if I just say exit? Is that 1 compute unit then? Having fun with assembly. We have a program needing 1 compute unit. Have you ever sent a transaction that used 1 compute unit? I did. It does nothing, but it has an instruction. It just doesn't do anything except say, exit. Nice. Very nice. I like this. This is so stupid. But yeah, I'm having fun with assembly. Good enough. I guess this is where I ended now, though. It doesn't get fewer than this. Also doesn't get less effective than this. It is literally doing nothing anymore. It's efficient, but not effective. Yeah, okay. So you don't want to optimize on efficiency. You want to still do the things that you want to do. But anyway, I hope that this video was fun to watch and that you learned something. I did. I now have a better understanding of what operations we actually have on Solana, like low level. And I wrote my own assembly program that does absolutely nothing but only takes one compute. Isn't that fun? Oh, so fun. Okay, good enough. There will be more content about low-level Solana development. So make sure you are subscribed. Give this video a like if you enjoyed it. Watch some other ones. And I will see you in a future video. Until then, write your program with one compute. Or a few. Do it as an exercise. It's fun. I like it. Okay, see you next time.